When people talk about the universe, they usually picture vast expanses of space, measured in billions of light years, that can be seen with radio telescopes. Alex Filipenko, University of California, Berkeley. They think of stars, galaxies, planets, and everything that surrounds them. Clifford Johnson, University of Southern California. Humans in space move by gravitational forces. Sean Carroll, Caltech. There are certain laws of nature, and it seems to you that they are eternal. But there is another universe, an invisible world that defines all things. When we study objects in the microworld trillions of times smaller than our familiar bodies, it turns out that the intuitive laws of the ordinary world no longer apply. The wonders of the microworld are seen in particles the size of an atom, that is, about 1/10,000,000,000th of a meter. These particles behave so unusually that scientists had to create special laws to describe their interactions. These laws were called quantum mechanics, and its postulates are truly amazing. Imagine that this ball is a subatomic particle, like an electron or a photon, which live according to the strange laws of the microcosm. Such particles can become invisible, pass through solids with ease, be in several places at once, and even seem to travel through time, changing the past. It's as if someone could throw this microscopic ball into two areas of the field at the same time, or go back in time and change the results of a game. So far, this is only possible in science fiction. However, we are certain, or almost certain, that this is how things work in the quantum world. And it's mind-boggling. And if scientists understand how quantum laws work, they will be able to harness their effects in the ordinary world, thus revolutionizing modern means of computing, and maybe invent a means of transmitting information over vast distances. Turning dreams into reality is a phenomenon called quantum entanglement. Already today, scientists are trying to put it at the service of civilian and military technologies. Fred Kuttner, University of Carolina, Santa Cruz. Quantum physics suggests that one object can instantly affect another, even if there are millions of kilometers between them. This is how it works. When two subatomic particles interact, they can become entangled, meaning that their speed and position and other characteristics become interdependent due to some processes unknown to science. Thus, if you change the quality of one of these particles, the other will also change instantly. Ideally, it is expected that quantum states of a particle are absolutely dependent on the quantum state of its partner particle. This means that if scientists observing the entangled particle make it spin clockwise, the other particle will immediately start spinning in the opposite direction. At first, such a discovery seems curious, and only curious. But let's think about it. It can be used to affect objects that are billions of light years away, and the effect on one object will have an effect on another. This phenomenon is amazing because it means that information can be transmitted instantaneously from one particle to another at superluminal speeds. I don't understand the essence of this phenomenon. No one does. This is the very mystical long-range interaction in Einstein's terminology. Alex Filipenko. Why are physicists so eager to put this strange aspect of quantum mechanics to the ultimate test? To explore the beginnings of the story, let's move to Brussels, the city where Albert Einstein traveled in 1927 to attend a meeting on a new theory describing the microcosm of atoms and tiny particles, quantum mechanics. Quantum mechanics is one of the most amazing intellectual achievements in human history. Sean Carroll. For the first time, scientists were able to prove the existence of a world that was previously completely invisible to us, by viewing the world on the scale of atoms and particles, smaller than a human hair. One way to imagine these scales is to take an ordinary object like a soccer ball, enlarge it to the size of the Earth, and then move to the planet. Then you find yourself in a world of atoms and particles. It was the nature of the fundamental particles that make up the world around us that Einstein came to discuss in Brussels. And it was here that Einstein engaged in the heated debate that led to the discovery of quantum entanglement, a concept that would trouble him for the rest of his life. This is the original Solvay Institute building, a beautiful grand building. It was here, in October 1927, that the 5th Solvay Conference was held. This amazing week-long series of discussions about what the world is made of, the nature of matter, and the new quantum theory. These steps are the same steps on which the famous group photograph was taken. This is a gathering of some of the most remarkable people in the world. In the front row, we see Albert Einstein and the great Marie Curie and Max Planck. In the back row is Erwin Schrödinger and those feisty 20-somethings, Werner Geisenberg and Wolfgang Pauli. These scientists were the pioneers of quantum mechanics. It was one of the greatest meeting of minds in history. More than half of them were or would become Nobel Prize winners. Their experiments showed that deep inside matter, tiny particles like atoms and their orbiting electrons were not solid little spheres. They seemed fuzzy and undefined. These people explored deeper and deeper, hoping to find the fundamentals of the world. To their surprise, they found that the world was becoming less and less solid. This world was not tiny bricks that were getting smaller and smaller, but some kind of substance. And what appeared to be solid actually became very messy and led to a whole new way of thinking about nature. The theory of quantum mechanics presented at the meeting was strange. It claimed that a particle such as an electron is not physically real until it is observed, measured by an instrument capable of detecting it. Before it is detected, instead of being a solid particle, the electron is just a fuzzy wave, a probability wave. These objects, like electrons and atoms, when we describe their behavior mathematically, the only thing we can describe is the probability of finding them in one place or another. It's like a wave of all the different possibilities. It's not that the electron is in one place or another. We just don't know. The point is that the electron is really a combination of all the possible places it could be until we look at it. Sean Carroll. Quantum mechanics only tells us the probability of properties of a particle, such as location. The laws of nature were no longer definite statements about what would happen next. They were just statements about probabilities. And Einstein thought, well, that's a defeat. You're giving up the essence of what physics was, which is a complete description of reality. For Einstein, the idea that particles only appear when they are observed was akin to magic. Outside the formal setting of the conference, he would challenge the most vociferous proponent of these ideas, the great Danish physicist, Niels Bohr. One day, Einstein would show up for breakfast at the hotel, and Niels Bohr would be there. Then Einstein would present his final challenge. Niels Bohr would start muttering and walking in circles, consulting with his colleagues, and after a formal meeting at the institute, by dinner time, he already had an answer. Einstein was like the devil out of a snuff box. Every day he appeared with a new challenge, and Bohr, by dinner time, to find the answer, and everything began again. For Bohr, his colleagues, quantum mechanics not only explained experimental results, its math was elegant and beautiful. And because Einstein found no errors in their equations, they left the Solve conference feeling more confident in their ideas than ever. But Einstein did not give up his conviction that quantum mechanics was wrong, and his refusal to accept the theory's strange conclusions led him to an even stranger discovery. In 1933, when the Nazi Party came to power in Germany, Einstein decided to settle in America and took a position at the Institute for Advanced Study in Princeton, New Jersey. He recruited two physicists to help, Nathan Rosen and Boris Podolsky. And in 1935, they discovered a possible error in quantum mechanics that would shake the foundations of the theory. They noticed that the math of quantum mechanics was leading to a seemingly impossible situation. Podolsky said, "Well, Professor Einstein, this is very important in your argument showing that quantum theory is incomplete." So a lively discussion began, and as is often the case among scientists, somebody suggested that they write a joint paper. And so they did. Their paper, known today as EPR, argued that the equations of quantum mechanics predicted an impossible connection between particles. It would be like having two particles, each hidden in a cup. When one of them was observed, the other, with matching properties, would mysteriously manifest itself. Quantum theory suggested that this effect could happen in the real world, such as with particles of light. Photons. The equations implied that a photon source could create pairs so that when we measure one particle, it emerges from its fuzzy state and another particle instantly pops out of its fuzzy state with correlated properties. The 1935 paper describing this effect became Einstein's most cited paper. It fascinated generations of physicists, including Anton Zeilinger. Anton Zeilinger said, "The first EPR paper struck me. I reread it 5 or 6 times to understand the point they were trying to make." Another way to imagine bound particles is to imagine a game of luck, which is somehow rigged. Let's take a pair of quantum dice. Let's place these 2 quantum dice in a bowl and then roll them. They show the same number, 6. Put them in again, and now they both show 3. Again, and they both show 1. We see that these two random processes show the same number. How can two particles act in unison, even when they are separated from each other? The important point in the EPR argument is that these particles can be separated by an arbitrary distance. One could be in Princeton, and the other in the Andromeda galaxy. And yet, according to quantum mechanics, the choice of measurement here somehow instantaneously affects what can be said about the other particle. You can't go from Princeton to Andromeda instantaneously. And yet, according to them, that's what the equations of quantum mechanics imply. And they said that this points out the flaws in quantum mechanics. The world just can't work that way. For Einstein, this strange effect contradicted the most basic concept we use to describe reality: space. For him, objects, particles, everything that exists is in space. Space, along with time, was a key element of his theory of special relativity with its famous equation, E equals mc squared. Einstein, of course, was the master of the space-time continuum. He believed that if something happens here, it should not immediately and instantaneously change something that happens there, the principle of locality, as we now call it. Sean Carroll. For Einstein, it's just common sense. If objects are separated in space, then for one to affect the other, something has to move between them, and that movement takes time. Quantum particles acting in synchrony could be explained if they exchange signals, one particle instantly sending a signal to the other, telling it what properties it should have. But that would require a signal traveling faster than the speed of light, which Einstein's theory of special relativity proved impossible, and it would have meant that particles were fuzzy and indeterminate until the moment they were observed. Instead, Einstein believed that particles must be real from the start. They should carry with them a hidden layer of underlying physics that determined their properties from the very beginning, almost like magic tricks that, though seemingly mysterious, have a hidden explanation. But this hidden physics was absent from quantum theory. So Einstein, Podolsky, and Rosen argued that quantum mechanics was incomplete. Podolsky was very enthusiastic about this project. In fact, he was so interested that he ran to the New York Times and told them the news. Einstein was very upset with Podolsky. It is said that he never spoke to him again. When Niels Bohr heard about Einstein's article, he wrote a vague response, claiming that one particle somehow mysteriously influences another. This seemingly impossible phenomenon became known as quantum entanglement, but Einstein dismissed it as spooky action at a distance. No one could devise an experiment to test whether Einstein or Bohr was right. But that didn't stop physicists and engineers from using quantum mechanics to create new things. In the 30s and 40s, the debate around EPR subsided, but quantum theory was actually gaining momentum. The math led to all sorts of amazing developments. Not counting entanglement, the equations of quantum mechanics allowed scientists at the Manhattan Project to develop the atomic bomb. And years after World War II, researchers at Bell Labs in New Jersey used quantum theory to develop one of the first lasers. The labs experimented with light, creating small devices that could control the flow of electricity. Transistors that would play an important role in our digital age. Transistors became the building blocks of the burgeoning field of electronics. Computers, hard disks, the whole digital revolution followed. All of this was made possible by the equations of quantum theory. However, Einstein's questions about entanglement and what this suggests about the incompleteness of quantum mechanics remained unanswered until the 1960s, when a physicist from Northern Ireland made a remarkable discovery. John Bell. Bell was a very talented young physics student, but quickly became disillusioned with what he saw as an almost certain dishonesty among his professors. Bell insisted that Einstein's questions about quantum mechanics were not being addressed. He got into fierce arguments with his professors. "Don't tell us that Bohr has solved all the problems. It really deserves further thought," he said. "Quantum mechanics has made fantastic progress." So, it's a very intriguing situation. Underlying all this spectacular success are big doubts. John Bell. Since the 1930s, however, the idea of sitting down and thinking hard about the fundamentals of quantum mechanics has been unpopular among professional physicists, and people who tried to do this were expelled from the physics community. So Bell had to do ordinary particle physics during the day, but at night, secretly, he could do the basics of quantum mechanics. Bell became a leading particle physicist at CERN in Geneva, but continued to research the debate between Einstein and Bohr. And in 1964, he published a startling paper. Bell proved that Bohr's and Einstein's ideas gave different predictions. If you could randomly take one of two possible measurements of each particle and check how often the results matched, the answer would show whether we lived in Einstein's world, a world that followed the laws of common sense, or Bohr's world, which was deeply weird and allowed for spooky quantum entanglements. We know now, looking back, that it was one of the most significant papers in the history of physics, not just in the history of 20th century physics, but in the history of the whole field. But Bell's article appeared in an obscure journal. The journal closed a few years later, and the article was not a central topic for the physics community. It was consigned to the library shelves and forgotten. A few years later, quite by accident, a brilliant experimental physicist came across Bell's article. I think it's one of the most amazing articles I've ever read in my life, and I kept wondering, gee, that's great, but where's the experimental evidence? John Clauser. John had worked on Bell's theory with physicist Abner Shimoni, and at the University of California, Berkeley, began work on an experiment to test it. He had a talent for building equipment in the lab and assembling the right parts. Step by step, John Clauser and Stuart Friedman created the world's first experiment to test Bell's theory. They focused a laser on calcium atoms, causing them to emit pairs of photons that, according to the equations of quantum theory, should be entangled. They recorded whether the photons passed through filters on each side and checked how often the results matched. If, after hundreds of thousands of measurements, the pairs were more correlated than Einstein's physics predicted, they should have been eerily entangled. John Clauser and Stuart Friedman saw the stronger correlation characteristic of quantum mechanics. The result was exactly as predicted by Bohr's quantum mechanics. The experiment showed that the spooky correlations of quantum entanglement do exist in the natural world. Had the great Albert Einstein been wrong? Surprisingly, the first people to react to this extraordinary result were not the world's leading physicists. A small group of free-thinking physicists at the heart of San Francisco's New Age scene contacted John. They called themselves the Fundamental Physics Group. They spelled physics with an F. Some members of the group experimented with psychedelic drugs. They were part of the hippie scene, and this group was fascinated by the question of entanglement. Their idea was just to discuss secondary topics in an open-minded way. They tried to connect Eastern mysticism with quantum entanglement. They sold many popular books. They had many followers. Their books became bestsellers, such as The Tao of Physics, which emphasizes that Eastern philosophy and quantum entanglement describe the deep interconnectedness of things in the universe. It was a great cosmic unity. The group held meetings at the iconic Hesselen Institute. It was a gorgeous, beautiful place where they discussed all these ideas. It was right on the Pacific Ocean, where streams of water from the hot tubs cascaded down the cliffs into the Pacific Ocean. As far as I know, no useful connections to Eastern mysticism were ever discovered by the group, but it was fun. John Clauser. The basic physics group may not have unlocked the secrets of cosmic unity, but by treating entanglement as a central part of physics, they were decades ahead of their time. Quantum entanglement is not only a fact of the microcosm, its effects can be seen and felt in the ordinary universe as well. If scientists ever manage to overcome a few major hurdles, quantum entanglement could allow humanity to transmit information over vast distances. Often, people think that quantum entanglement, the key to realizing the long-held dream of transmitting information over vast distances at superluminal speeds. I don't think that's possible. After all, these systems would have to be built at lower speeds anyway. But how can I know everything? 100 years ago, going to the moon seemed impossible. More likely, quantum entanglement will change the current means of data processing. Scientists hope it will help design more powerful computers. Massachusetts Institute of Technology, Professor Seth Lloyd, helped create a prototype quantum computer that uses quantum bits instead of conventional bits to store data. This lab has developed superconducting quantum bits, or qubits. By learning how to do quantum computing with qubits, we will be able to create multitasking quantum computers that can perform a huge number of operations simultaneously. They will get 4 simultaneously by adding 2 and 2, 1 and 3. The fact that even a single qubit can perform many calculations makes a potential quantum computer the most powerful ever created by man. Of course, this project is under development, Much like traditional computers in the 1950s, these machines, too, take up huge rooms and can only perform basic operations. But they hold a lot of promise. Quantum physics is known for being unusual, counterintuitive. Quantum computers are the same, but they can do things that are beyond the reach of ordinary machines. So far, the most serious problem remains the efficient encoding of information in such computers. The classical binary system is being tried to be translated into a system of quantum entanglement. When scientists succeed, humanity's life could change dramatically. Even if a quantum computer has a small amount of memory, it could be used to crack all existing internet codes or solve the most complex equations with a colossal number of variables, such as those that describe the Big Bang. Seth Lloyd. Decades later, advanced laboratories around the world now seek to harness quantum entanglement to create revolutionary new technologies, such as quantum computers. In our everyday computers, the basic unit of computation is a bit, a binary digit, a 0 or a 1, and inside the computer, there are all these transistors that turn currents on and off. On is a 1, off is a 0, and these combinations lead to universal computation. Working with a quantum computer, you start with a fundamental unit, which is not a bit, but a quantum bit, which is neither 0 nor 1, but can be volatile. The quantum bit exploits the fuzziness of the quantum world. A qubit, as we know, can be 0 or 1, or a combination of both. A particle, or a tiny quantum system, can be converted into a qubit, and today, it's not just pairs of particles that can become entangled. Groups of qubits can be linked using entanglement to create a quantum computer, the more computing power. At Google's Quantum Computing Lab in Santa Barbara, a team recently succeeded in creating a tiny chip that contains an array of 72 qubits. Researcher Marissa Gayustina and her colleagues send signals to these microscopic qubits to control and entangle them.
Mounted on the underside of this plate, we have the quantum processing chip itself. In essence, a quantum playground, you could say.
You could say that each qubit is a quantum object that can be controlled at will. Using entangled qubits, quantum computers can solve real-world problems that traditional computers simply cannot handle. For example, a salesman needs to visit several cities, and he wants to find the shortest route. Sounds simple, but with only 30 cities, there are so many possible routes that it would take a conventional computer, even a powerful one, hundreds of years to try each one and find the shortest one. But with a few entangled qubits, a quantum computer could find the optimal path in far fewer steps. There's another reason why teams like Marissa's are striving to build a powerful quantum computer: breaking secret codes. In today's world, everything from online shopping to secret military communications is protected from hackers using secure digital codes, a process called encryption. But what if hackers could gain access to quantum computers? A quantum computer can break the best encryption protocols in minutes, whereas a regular computer or even a supercomputer network would fail in months. While quantum entanglement may pose a threat to traditional encryption, it also offers an even more secure alternative: a communication system that the laws of physics themselves protect from hacking. Researchers in China are leading the way in this area. At Shanghai's Jianwei Pan University of Science and Technology, he runs a leading center for quantum research. His teams are working to harness the properties of the quantum world. They can send secret messages using a stream of photons in a system that instantly detects any attempt at eavesdropping. Jianwei Pan's team has created a network of optical fibers, more than 1,000 miles long, that can transmit secure information from Beijing to Shanghai. It's being used by banks and data processing companies. But there is a limit to how far quantum signals can be sent through the optical fibers. To further transmit signals, Jianwei Pan's team launched the world's first quantum communication satellite. There are fewer obstacles above the Earth's atmosphere, and quantum particles can travel much farther. Every night, teams on the ground prepare to track the satellite across the sky. Laser guidance equipment locks onto the satellite and allows them to send and receive signals. The team aims to use this equipment to create a new secure communication system using quantum entanglement. The satellite sends entangled photons to two users. An eavesdropper can intercept one of the entangled photons, measure it, and send a new photon. But it won't be an entangled photon. Its properties will not match, and it will be clear that someone was on the line. In theory, the technique could be used to create a fully secure global communications network. The next step will be to set up ground stations, for example in Canada and in Africa and elsewhere. We will use our satellite for global quantum communication. We want to push this technology as far as possible. Jian Weipan. These are the first steps in creating a completely invulnerable quantum internet of the future, made possible by quantum entanglement. But there's a problem. What if quantum entanglement, spooky action at a distance, isn't actually real? It could mean that entangled photons are not a path to total safety. The question goes back to John Clauser and Stuart Friedman's experiment to test Bell's theory. Years after their groundbreaking work, physicists began checking for possible loopholes in their experiment, ways in which the illusion of entanglement could be created so that the effect wasn't so spooky. One loophole is particularly hard to pin down. In current experiments to test Bell's theory, devices on each side test whether photons can pass through one of two randomly chosen filters. In effect, they ask one of two questions and test how often the answers match. If, after thousands of photons, the results show more coincidence than Einstein's physics predicts, the particles must be eerily confusing. But what if something mysteriously affected the equipment so that the choice of filters wasn't truly random? Could there be some common cause that existed deep in the past, even before the device was turned on? That could have prompted the question and the types of particles emitted. Could it be that some strange particle, some force that has not been accounted for, something that looks like entanglement, could really be a fluke, an illusion? Maybe the world still works the way Einstein thought it did. It is this loophole that a team at an observatory in the Canary Islands is working on. Since quantum mechanics is now better known than ever, they are determined to put entanglement to the ultimate test and finally resolve the Einstein and Bohr debate beyond any reasonable doubt. The team creates a giant version of the Clauser and Friedman experiment, using the entire universe as a laboratory. In this Bell space test, the source of the entangled particles is about 1/3 of a mile away from each of the detectors. The team must send perfectly synchronized pairs of photons through the air to each side at the same time. The telescopes will collect light from two extremely distant, extremely bright galaxies called quasars. These are some of the brightest objects in the sky, emitting light in powerful streams. Random variations in this light will govern what filters are used to measure photon pairs. And because quasars are so far away, the light traveled billions of years to reach Earth. This makes it extremely unlikely that anything could have affected the random nature of the test. If the experiment is successful, the team will eliminate the loophole and prove that quantum entanglement is as creepy as Bohr always claimed. Now that the telescopes are tethered to two different quasars, the team begins to make measurements. The light from the quasars determines which filters will be used to measure the entangled photons. It's exciting, but it's not yet clear what the results will be. 2 months later, back in Vienna, the team is analyzing the experimental data. This may take some time. The results show confusion, and since the light from the quasars that drove the test was almost 8 billion years old, it is highly unlikely that anything could have affected its random nature. This remaining loophole appears to be closed. The big cosmos is reduced to the control of a small quantum experiment. That in itself is a beautiful thing. Honestly, I still get goosebumps when I realize what our team was able to accomplish on this intellectual journey that goes back to the early years of the 20th century. There was hardly room for an alternative explanation like Einstein's. We didn't rule it out, but we stuck it in such a tiny corner of the cosmos that made our results even more improbable for explaining anything other than entanglement. David Kaiser. Accepting that entanglement is part of the world around us has profound implications. It means that we must accept that an action in one place can have an instantaneous effect anywhere in the universe, as if there were no space between them, or that particles acquire physical properties only when we observe them. Or we must accept both. We are left with conclusions about the universe that make no sense at all. Science goes beyond all bounds of common sense. It's almost like Alice in Wonderland, where anything is possible. At first, it was seen as an undesirable but inevitable consequence of quantum mechanics. Now, after nearly a century of controversy and discovery, spooky action at a distance is finally at the center of modern physics. At the Institute for Advanced Study, where the concept of entanglement was first described, Researchers are now using it in the search for a unified theory of the universe, the holy grail of physics. Einstein's theories of special and general relativity perfectly describe space, time, and gravity on the large scales of the universe, while quantum mechanics perfectly describes the tiniest scales. However, the two theories have never been unified. So far, we have not had a single complete theory that is both quantum mechanical and reproduces the predictions of Einstein's remarkable theory of relativity. Perhaps the secret is entanglement. Sean Carroll. What if space itself is actually created by a tiny quantum world, just as temperature, warm and cold, consists simply of the movement of atoms within an object? Perhaps space as we know it arises from networks of entangled quantum particles. It's a staggering idea. We may someday have to give up what Einstein called sacred, namely space and time. He always thought, well, we have little bits of space and time, and we build the whole universe out of them. In the radical theory known as the holographic universe, space and time are created by entangled quantum particles on a sphere that is infinitely far away. It may be impossible to intuitively understand this wild mathematical idea, but it suggests that entanglement may be what forms the true fabric of the universe. The most puzzling element of entanglement, the fact that 2 points in space can somehow communicate, becomes less of a problem because space itself disappears. In the end, we're just left with this quantum mechanical world, and space no longer exists. Thus, the paradoxes of entanglement, the EPR paradox, dissolve into thin air. A true understanding of quantum mechanics will only come when we put ourselves on the side of entanglement, when we stop favoring the world we see and start thinking of the world as it really is. Science has made tremendous progress over the centuries by breaking complex systems apart. When we encounter a phenomenon like quantum entanglement, that scheme collapses. When it comes to the basics of quantum mechanics, the whole is more than the sum of its parts. The primary motivation is simply to learn how nature works, what's really going on. Einstein said it very well. He wasn't interested in this detailed question or that detailed question. He just wanted to know what God was thinking when he created the world. It's hard to believe, but the microcosm can hold more amazing surprises. The most famous experiment in quantum physics demonstrates how a single object can be in two places at once. The experiment once amazed Einstein himself. By exploring the microcosm, scientists have proven the possibility of phenomena that do not occur in the ordinary world. In the universe of the smallest particles, not only information can propagate at superluminal speed, but the very fact of observation can change the result of the experiment. It seems that the behavior of particles changes depending on whether we're watching them or not. Sean Carroll. This profound observation was made as a result of Young's experiment. Scientists first conducted it 100 years ago by passing photons through a metal plate with two slits. The particles that slip through the slits illuminate a projection screen behind plate. The screen would be illuminated as if waves were being passed through the slits in the barrier. It would pick up the phenomenon of interference. But we've always assumed that electrons are particles. Why do they behave differently? The results of the experiment were baffling. The electron was a particle until it was launched into the screen. After that, it left a trace on the projector, as if not one electron, but two had passed through the slits in the barrier. Did the microparticle somehow clone itself? Years of research have not brought scientists any closer to answering these questions. Fred Kuttner. Maybe the most puzzling phenomenon in quantum physics is that one object can be in two places at the same time. It's as if the electron senses both slits and goes through them, senses at some quantum mechanical level of its own. Clifford Johnson. Most scientists are confident that there is a rational explanation for this phenomenon that can be experimentally proven. But still, that explanation has yet to be found. In an attempt to understand exactly how a particle can be in two places at once, scientists began to observe how a single electron would behave when it was passed through an obstacle with two slits. How can a particle pass through both slits at the same time? The physicists followed the motion of electrons, photons, and other subatomic particles regardless of their size. This is completely inexplicable. The outcome of the experiment depends on whether or not the experiment is monitored. In the first case, the behavior of electrons is similar to the movement of balls. In the second case, to the movement of waves. But all this does not happen at the same time. scientists have become confused. It seems that the process of observation was affecting the nature of subatomic particles. Surprisingly, when we don't observe objects, they are waves. When we observe, they are particles. And even electrons, which everyone thought were particles, exhibit wave properties when they're not being observed. Sean Carroll. This fact, that the nature of a particle varies depending on whether it is under observation or not, is called the quantum uncertainty principle. How can our decision to make an observation change the behavior of an object? There is one technical explanation. In order to do research, you have to interact with the system in some way. You point a beam of light at it and see its reflection. That's how we determine that a baseball is in a particular location. We see the light reflected off of it. When it comes to large objects, observations are almost undistorted. But particles in the microworld are very sensitive to light, which can change their behavior. In microworld space, photons are about the size of subatomic particles and can have a significant effect on them when we point light at a system to view it. However, it's not entirely clear why light doesn't just change the direction of observed objects, but their very nature. The answer is simple. We don't know. This is the basic mystery of quantum mechanics, the reason why this science is so complex. If you look at an object, you see a particle. If you don't look, you deal with a wave. We scientists have been arguing about this for 100 years, but we can't come to an agreement. Max Tegmark, when the results of the experiment were published, centuries ago, the greatest minds in science were confused. Einstein said, "I don't believe in quantum physics because the moon is in the sky even when I'm not looking at it." Einstein, of course, in this case, compared objects fundamentally incomparable. After all, the existence of the moon does not depend on whether you observe it or not. However, the story of Young's unfathomable experience did not end there. In recent years, the development of technology has allowed scientists to develop a new version of this experiment, which has changed our very perception of time. This is a kind of high-tech version of the famous experiment. Electrons were still passed through a barrier with two holes. However, now scientists were able to make observations when the electrons had already passed through the hole, but had not yet hit the projection screen. It's as if you were standing on a baseball field near the barrier, with your eyes closed, and the balls were flying through the holes and behaving like waves. But at the last second before impact, you would suddenly open your eyes. At that moment, the electrons become particles, as they were when launched from the electron gun. The electrons behave as if they've gone back in time, as if they didn't go through two holes, but only one, as if they never exhibited the properties of a wave. It doesn't settle in my mind. That's the mystery. How does our decision to do the experiment affect the nature of the electron? One way or another, it's an influence we exert, thereby observing the possibility of traveling back in time. Fred Kuttner. Scientists are just beginning to explore the practical application of the discovery. But what is clear is that the laws of the subatomic world may reveal the universe to us from a perspective that resembles a science fiction story. Maybe quantum physics will show that all our reality is just a figment of human imagination. After discovering the mysteries of the microcosm, scientists wanted to unravel and explain as soon as possible. However, when they tried to understand what exactly was going on in the world of subatomic particles, something unexpected happened. Nature refused to show them. When we investigate the microcosm, it turns out that almost all the basic objects in it are hidden by a veil of uncertainty. And this is not because of flaws in our methodology, but because nature itself has not made up its mind about some things. Scientists call it the uncertainty principle, and despite the strangeness of it all, maybe this is the basic principle of our world's existence. We simply cannot know anything with absolute certainty. In our daily lives, we think we know a lot about the objects around us. We can, for example, locate a billiard ball and hit it with a certain force, collide it with other balls by directing them into the hole. But what happens in a world a trillion times smaller than ours, where such billiard balls are subatomic particles? Turning to the microcosm, physicists realize that they are simply unable to accurately locate particles because of their wave properties. And more surprisingly, when scientists try to catch a particle, it generates energy and leaves the observational space before its location and velocity can be determined. The uncertainty principle states that nature does not allow its fundamental particles to be caught, because particles in the microcosm interact according to their own special rules and laws. Billiards there becomes a completely different game. The uncertainty principle in the microcosm applies not only to the location of a particle, it applies to everything, including the energy of particles. This startling phenomenon has been called quantum tunneling. According to classical mechanics, if you throw a ball at a wall not hard enough, it won't penetrate it and will bounce off. However, when it comes to an electron, it turns out that it can pass through matter, even if it was thrown not hard enough. And how can that be? It probably sounds incredible, but the uncertainty principle at work in the microcosm allows a particle to borrow energy from the future to overcome a barrier and then give it back. In fact, the potential electron is already on the other side of the wall, which is why it can overcome it. Fred Kuttner. Ever since the astounding properties of the microcosm were discovered 100 years ago, people have constantly asked whether the phenomena of quantum tunneling, being in more than one place at a time, of going back in time, can be applied to the ordinary world. Some scientists categorically reject this possibility. A baseball is made up of a huge number of particles, and it would be necessary for all of them to suddenly disappear in one place and reappear in another, for example, behind a solid wall. That's hardly possible. Only one electron or one proton can do that. The larger the particle, or the larger number of subatomic particles, the more complex the tunneling process. However, a growing number of physicists are coming up with even more sensational theories to explain what is happening. It is known that tiny subatomic particles can be in two places at the same time. But actually, I myself am made up of these particles. If they can be in two places at once, so can I. Max Tegmark. Scientists call this the many worlds interpretation of quantum physics. They argue that, like the electron, people live several different lives in parallel. Every time we are faced with a choice, we do not choose one version of events, and we only exercise both in different dimensions of our reality. In fact, whenever you focus your mind and will on choosing something, you are simultaneously choosing several possibilities, and all of them are realized in different parallel universes. Max Tegmark. The many worlds interpretation of quantum physics states that all potentialities are realized in multiple parallel universes at the same time, specifically parallel universes. That's how things could be. These startling hypotheses of theoretical physicists may sound implausible, but this is how the microcosm lives. So, there is a parallel universe. If you take quantum mechanics as axiomatic, it means that every time you do a Young's experience, there are, as it were, two copies of you. The first one gets one answer, the second one gets a different answer. It follows from this that every time in a choice situation, there are many copies of you in parallel universes. Today, it is generally recognized that the microcosm conceals many oddities. Many people are sure that their action does not extend beyond this world. That is why such large objects as people are not able to be in two places at the same time. But it's now clear that such notions are naive. The properties of the microcosm can manifest themselves anywhere. The very interesting debate about the many worlds interpretation of quantum physics will continue until scientists unravel the secrets of the microcosm. However, a number of astronomers believe that this is unlikely to ever happen. According to their calculations, a huge number of objects that make up our universe exist not in the three dimensions we are accustomed to, but in some other dimensions that are inaccessible to us. But if there is anything in the microcosm that is stranger than quantum particles, it is a special kind of matter that scientists have never seen in person, but which has played a key role in the formation of planets, star systems, and galaxies. Astronomers know that there is invisible matter that exerts a gravitational influence but is not visible. We call it dark matter. Alex Filipenko. Without dark matter, we would not exist, because it is thanks to it that various vital structures are formed, including galaxies. Dark matter accounts for about 85% of gravitational interactions in the universe. If dark matter is made up of particles, it means that millions of them pass through us every second. But even knowing dark matter exists, astronomers still can't say what it is. At first, they thought it was a familiar kind of matter that they couldn't see for some reason. While astronomers are making a description of it, we know how much ordinary matter there is in the universe. By it, we usually mean atoms, which are made up of protons, neutrons, and electrons, the elementary particles that form me, you, everything on Earth. But that's just the very tip of the iceberg. There's too little of this kind of matter. That conclusion stunned everyone. How could it be? It's a shocking discovery. It turns out that the familiar atoms are only a small part of our world. The rest of the matter, which is 6 times more, is completely invisible to us. It's funny that science has brought us to a point where we realize that not only are we not the center of the universe, but we're not even made of the same matter as the bulk of it, because the bulk of it is dark matter, which is made up of tiny particles that we can't see. Sean Carroll. Some theoretical physicists have speculated that dark matter may be made up of neutrinos, particles 1,000 times smaller than electrons, whose properties are very similar to those of dark matter. We know that neutrinos exist. They have mass and weight, so the delusion is explainable. But still, dark matter is not neutrinos. Dark matter cannot be made entirely of neutrinos because they move very fast. They destroy the large-scale structures that formed our galaxies at the very beginning of the history of the universe. So galaxies simply wouldn't have appeared if dark matter was saturated with lots of neutrino particles. So, dark matter is unusual. It doesn't have neutrinos. It's made up of some particles as yet unknown to science. Subatomic particles probably appeared right after the Big Bang, when the universe was still hot and compressed. Their diversity must have been quite significant. Some of them disappeared, some underwent transformations, but some remained unchanged. So what are they? Since physicists do not provide an answer to this question, astronomers propose a hypothetical particle that has all the characteristics of dark matter as a candidate. They call it WIMP, Weakly Interacting Massive Particle. The problem is that we've never been able to detect WIMP in the lab. Right now, there are experiments going on in several underground laboratories to find WIMP, mostly big particle gas pedals like the Hadron Collider in Geneva. Thus, there are several strategies for detecting these objects, if they exist. And if scientists prove the existence of dark matter, would that mean the possibility of dark parallel planets, dark life forms, a dark Mendeleev table? I don't think dark matter particles can form planets like the ones we observe. If they could, the characteristics of our solar system would be different. I think it's more likely that dark matter particles have a different, more complex nature than ordinary objects in the microworld. Max Tegmark. However, modern science has yet to find any trace of these mysterious particles. So more and more scientists believe that the problem is not what these particles are, but where they are. Could they simply be in other dimensions? Some are quite seriously claiming that dark matter came to us from other dimensions, or are just ordinary particles, just in other dimensions. After all, we do not see other dimensions, nor do we interact with them, so why can't dark matter be lurking out there? Perhaps the gravitational interactions of galaxies and galaxy clusters are caused by dark matter, which is concentrated in other dimensions and cannot be discovered in our dimension simply because it is unattainable. The result of its action can only be felt, but nothing more. In any case, many physicists are confident that someday they will understand the nature of dark matter, the particles of which are so incredibly small that it is impossible to see and study them yet. But what are the smallest objects in the world? The smallest particles in the universe are subatomic particles, like electrons and quarks. The latter are made up of protons and neutrons. It's now believed that they're all tiny vibrating strings, clumps of energy, and that these are the smallest objects from which everything is formed. Scientists have only just begun to try to study strings and other incredibly small objects in the microcosm, and their results are lifting the veil of mystery over our universe. As we delve deeper into the structure of the atom, scientists are gaining a better understanding of its mechanisms. But what happens if we go even further and try to study structures even smaller than subatomic structures? Structures smaller than an electron are unexplored realms, even more mysterious than star systems or galaxies. Stars, galaxies, planets we can observe. But where can we find the kind of instruments that can help us study the tiny objects that exist in our space and time? An analogy can be made. The microworld is a tiny, almost jewel-like instrument that, when handled properly, can help us achieve astonishing scientific results. Clifford Johnson. But scientists' attempts to explore space smaller than an atom have been unsuccessful, largely because of the struggles of humanity's weak technological base. To view an object in detail requires more energy. To see incredibly small particles is possible with incredibly powerful instruments. We study the elementary particles that are produced when other elementary particles collide at different energies. By increasing the energy supply of colliders, we can study processes that are faster and faster and particles that are smaller and smaller. Today, however, even the largest gas pedals do not have enough power to study the smallest known particles. But physicists are sure something exists out there at unimaginable depths that the human mind cannot even imagine. Scientists are trying to figure out what the Planck length of 10⁻35 centimeters is. It's several tens of times smaller than the size of an electron. Compared to it, the electron is simply enormous. The Planck length is almost unbelievably small. Objects of this size are almost impossible to study, although physicists try. That's the size that string theory operates on. According to this theory, the elementary particles of our world are small vibrating strings. To realize how small they are, let's take a pipette. Drop one drop of water. It has trillions and trillions of hydrogen and oxygen atoms in it. Now, imagine you took an atom of hydrogen and enlarged it 10 billion times to the size of half a meter. You ask, can we now see strings in the hydrogen atom? The answer would be no. We can keep enlarging it until it's the size of the solar system, but we still won't see the strings. Only when the atom is the size of the observable universe will we see strings. And what's really amazing is that we can even imagine it. But scientists are not just able to imagine it. They are also formulating various theories for such small particles. Perhaps this is a kind of holy grail for our science. Max Tegmark. We think that familiar space and time disappeared around the Planck length, but we don't know what appears in their place. We need to replace the concept of space with something more fundamental, something that can include a huge number of dimensions. Maybe this space is like a soccer field, where there are certain content zones with nothing in between. Maybe time at about a Planckian in length doesn't flow linearly, but jumps from one point to another. It's as if quantum particles are bouncing along the paths of the lattice, bypassing the space between them. Why? Because there is no space between them. It doesn't exist. Seth Lloyd. Be that as it may, most scientists believe that the familiar space and time at such lengths is changing into something else, somehow shrinking. Perhaps space and time take on independent properties, and in the case of extremely small distances and time intervals, loses all its importance and necessity, do not play any role. Scientists suggest that conditions at Planck distances are similar to those that existed before the Big Bang, when all the matter of the universe was concentrated in a microscopic point. Maybe the answers to the question of what the micro-world universe looks like are the same as the answers to the question of what the universe looked like before the Big Bang. Did this explosion put our universe at the beginning? Or did it simply change some pre-existing form of matter organization? There are no answers to all these questions yet, but they are believed to be somewhere in the depths, at the Planck distances. It may seem that the Planck length has nothing to do with our macrocosm, but it doesn't at all. It is our roots, our hidden universe, which a few billion years ago was even smaller than the Planck length. Whatever exists in the world of subatomic particles, according to whatever laws it evolved, scientists claim that by understanding this world, they will better understand the cosmos and the processes that took place just before the Big Bang. The space of the microcosm contains mysteries that await their explorers.